In this section, we're going to turn away from central tendencies just for a little bit to talk about what they mean and how we can talk about them. And we're going to focus on measures of variance and how things deviate, how things vary from one data set to another, from one data point to another. Well, some titles we have to look at here are standard deviation and standard variance. The key to notice here is that we have some symbols that have to be sort of remembered. Just like we had for x bar and mu, the difference between the sample mean and the population mean. Well, now we have these symbols over here, which represent my population, and over here that represent my sample. So notice again I have that Greek letter. This is a lowercase sigma. It's a little circle kind of with a tail on the end of it. And then for variance and deviation for the sample, I have just a lowercase s. Notice the relationship between the two. Variance is just deviation squared. Variance is not going to have a ton of meaning at this point. It will a little later in the year. We're going to talk about deviation, but variance is the path to get to deviation. If you were going to find this out by hand, you would have to find the variance, take the square root, and that would give you deviation. Luckily, we have the TI Inspire to do the steps for us, which we'll talk about more in class. So what are the uses of the standard deviation and standard variance? Why do we have it? So some of the uses are to check the consistency of values in a data set. The smaller the standard deviation in regards to the mean, keep that in mind, in regards to the mean, the smaller the standard deviation, the more consistent, the more compact the data set is. We can determine percentages in a certain interval. We'll look at that in the next two slides talking about Chebyshev's theorem and the empirical rule. And we can also use it to make predictions. One thing to keep in mind, standard deviation is always connected to your mean. It is not connected to your median. So let's move on to something different. So now we're talking about Chebyshev's theorem. And Chebyshev was a famous mathematician. And what he looked at was the idea that we want to figure out what percentages are within a certain interval. Well, Chebyshev's theorem is based on the idea that we do not have or do not know that we have a symmetric distribution. So this would apply to all distributions. And the formula 1 minus 1 over k squared, and then that value times 100%, that's going to tell us the percentage of values that fall within a certain interval, but it's going to be tagged with the word at least. So we might say at least 75% or at least 89%. In this formula, k represents not the standard deviation, but the numbers of deviation you are away from the mean itself. So let's look at an example down here. So if we know we have a mean of 50 and a standard deviation of 5, if we went one deviation forward and one deviation backwards, which would simply just be subtract 5 and add 5, we would end up with an interval from 45 to 55. If we went back another deviation, we'd get 40 to 60. If we went back a third deviation, we would get 35 to 65. So let's look at these three intervals for a second. In the first interval, since I'm one deviation away, my k value would be 1. In my second one, 40 to 60, my k value is 2. And in my third, my k value is 3. So now that we know our k values, we can go back and plug those into the formula. Well, if I go back and plug it into the first formula, I'm going to get 1 minus 1 over 1 squared. Second one's going to be 1 minus 1 over 2 squared. And then 1 minus 1 over 3 squared. So when we put those in, multiply by 100%, we're going to end up with some percentages here. So go ahead and do that. And I'll put the numbers up here in a second. And these are the percentages I got. 0% when I plug in 1, 75% when I plug in 2, 89% when I plug in 3. We have to add the word at least in here. So what we're saying with the at least is, let's just jump down to the bottom. The first one doesn't make any sense because we're talking about at least 0%. If we look at k equals 2, 40 to 60, at least 75% of the population will fall between 40 and 60, given the fact that my mean is 50 and my deviation is 5. between 35 and 65, at least 89%. It could be 100%, but it will be at least 89%. Let's move on to the empirical rule now. The empirical rule, when we talk about it, the idea behind this is symmetry. If you look down here, it's all going to be based on your x bar value or your mu. So this is all based on the population mean. And just like with Chebyshev's, we're going to add a deviation, subtract a deviation, add a deviation, subtract a deviation, and so on and so forth. And that's going to give us a window. But this is for symmetric data now. This is going to be also known as the 65, 95, 99.7 rule. And that's because if we go one deviation left to one deviation right, so if we look at here to here, that's going to represent 68% of my data, with 34% on both sides. If we take from here to here 2 deviations away, that's going to be 95% of my data. And if we go 3 deviations away, and I'll put this down the bottom here, that's going to be the 99.7% of my data. And we're going to look more at this in class and ask ourselves, how can we use the symmetry? How can we use this empirical rule? Because this idea, this normal distribution idea, is going to be a major backbone concept for us. Here's a little different look. When I break this down, you can actually see where all the numbers come in. And if you take a second, pause the DVD for 1 second, and go ahead and write those values in so we have those, the 34s, the 13.5s, and so on and so forth. And then we'll move on to Pearson's coefficient. Last thing we're going to look at is Pearson's coefficient of skewness. This is a number that's kind of lost anymore in statistics, but let's check it out anyway, just to get a feel for what skewness talks about. So let's look at 2 different examples. The 2 examples we're going to look at, in the first one here, we're talking about a mean of 80 and a median of 77, so the mean's a little bit higher. Well, if I go back and plug into the formula right here, I'm going to end up with a positive 2.25 for my skewness number. When we talk about skewness, anything beyond -1 and +1 is probably going to indicate that there's some skewness in the population distribution. Since positive 2.25 is outside of that interval, -1 to +1, we're probably looking at some kind of a skewness, probably in this case a pretty substantial skewness in the population distribution. And since it's on the positive side, we're looking at the idea that this distribution is skewed to the right. The other example, 80 being my mean, 81 being my median, and now my deviation's 4. The median is a little bit higher than the mean in this case. Plugging in my data is going to end up being a negative 0.75. Because this value is relatively small, it's inside the -1 to +1 range interval, we're talking about maybe a slight skewness to the left-hand side, but this would be relatively symmetric. So remember, -1 to +1 is kind of going to be my idea of anything in between that's probably going to be relatively symmetric. Outside of that, we're talking about some skewness. Again, like the other topics, we'll focus on this more in class.